Now, today we'll start with the next topic under the same case. This is called as the steady state error. Okay. Okay. Now, we already have discussed about a concept wherein we have seen that the output of any system will be split into two parts normally, like this concept. Okay, I'm coming back. So the one part which actually has yeah, this one. So if you have an equation, I'll just quickly recall what we had done in the disturbance analysis. So you have a system equation denoted by h of s, give an input r of s. So the output c of s has basically two parts, right? One part which is coming directly from the poles of the system. Okay, that part of the system which is a result of the poles present in the h of s or the transfer function is right, they are called as a system poles. Sorry, the output that results from the system poles is what is called as a transient. Okay. And there is another part, that is that part of the output is because of the input we give, right? Input has a pole called as excitation pole, right? The result that comes because of the excitation pole is called as the steady state, right? So we already have seen this, and we also have observed one thing: when the time goes to infinity, right, only the result because of the steady state exists, and the transient response will definitely become equal to zero. Okay, so far what this is what we know about the output of any system for a given input, right? So steady state, the word already has been coined here, right, which is the output of the system when the time goes to infinity. Okay, so now our intention is to look at the steady state error. It's not the steady state output, it is the steady state error, right? So if the output is simply the steady state output, it means that part of the output which remains after all the transients vanish. Correct. But there could be an error in our output, right? So steady state error in the sense, right, out of the, we expect a specific output value, right, when the t goes to infinity, but it is always not true that you get the desired output, right? You get an actual output which is away from the desired output, right? So the steady state error, this is denoted by ESS, E for error, SS for the steady state, right? So this actually denotes far uh, how far we are measuring, how far away the actual output uh, from desired, right? So we can try to measure this. So E steady state is desired output minus the actual. Okay, so the error signal is, now let's try to write for both cases. We have seen the feedback system and without feedback, okay, or a different feedback, right? So from the equation, or let's look at a block diagram first. So if I use this first, this is the output, say C of S. Let's say we have a feedback denoted by H. Okay, so this is the input R of s. Now this is the error. Okay, because plus minus this is input that is coming, and you are subtracting something, right, from that, because since you subtract that, you get the error defined in that way. Now, so what is the error? Now E of s is equal to, E of s could be written in the following fashion, right? So the error E of s is equal to, normally this should be the C of s. I have to I have a C of s as output, R of s as the input. We can write it as the input, that is R of s minus C of s. C of s gets multiplied by h while coming back. Okay, so that's why I need to multiply this with. All right. Now, fine. So let's try to write an equation properly, right? From this, let out of which, what is C of s, right? So I know what is C of s. So C of s is equal to, this is E of s into G of s, correct? Because the error gets multiplied by G of s to get the C of s. True, right? Therefore, so equation number one I'll change now. So this equation, therefore the E of s is equal to, there is R of s minus, instead of C I'll write E once again. This is E into G into H. To take the term containing E to the same side. So this implies the E of s, I can take it out. There is 1 plus E has gone out. So G into H remains, right? G of s into H of s is equal to R of s. Okay, so this implies, now we can try to represent the error signal in terms of the input. Input is R of s divided by 1 plus G of s into H of s. Okay, fine. So now we have one theorem, that is using the Laplace representation, because we are in the S domain. So the steady state error is defined as, we know that, as the limit t tending to 0, not 0, sorry, t tending to infinity, time becomes very large. What is the E of t? So, but we have a final value theorem of Laplace. So this says that this can also be calculated. The ESS can also be calculated by using the limit s tending to 0. This is s into f of s. Not f of s, in this case it is E of s. Okay, s into E of s. Right? Where we should know what is the E of t and corresponding E of s. This is what should be known, right? Once we know this, we can definitely apply this. Okay, so that is the requirement here. So for E of t, its Laplace is E of s. Now, without calculating E of t, how to calculate E of s, we know that, that's already written here. This implies I can substitute this over here. Okay, substitute this, and let's say, therefore the equation ESS is equal to, in terms of the block diagram representation, where we know different components like forward path, reverse path, or the feedback gain, etc. Once we know that, we can directly write this. Therefore limit s tending to 0, I have to multiply by a s here, right? So to the E of s, I should multiply by s. So this gives me s into E of s is simply R of s divided by 1 plus G of s into H of s. So the ultimate equation that we are going to remember to calculate the steady state error looks like this. So it's very clear that the steady state error of the system depends upon the following, right? it depends upon the R of S. What is R of S? It's the Laplace transform of the input. So if you the error changes with the input, that's what it makes sense now. So if you give a very complex input, maybe there is a lot of error, right? If you give a simple input, say e to the at or simply u of t, or right, anything very simple, it could be very less. Okay, and also it depends upon the g into h, right? So depends even on what type of feedback you are using and what are the uh, g of s and h of s. So all these matters when you try to represent the uh, whole function to calculate the e of s. Okay, this is the equation for e of s. Now we'll see the variety of the e of s that could result. Okay, now let's try to calculate the what do you call okay, let's try to calculate the steady state error, right, for different inputs. Okay, so this is what is very important, because we know that there are standard inputs, right, to the system, right? Why do you need a standard inputs defined? The standard inputs are defined because, right, we our intention is to look at the response of the system for various disturbances, correct? When you have a variety of disturbances coming into that could arise inside the system or outside the system, how the system responds we wanted to know, correct? So find ess, right, we use the standard inputs. So use standard input. What are the standard inputs? If you remember, uh, okay, let's try to write the unit, the values now. So first one is unit step, right? So unit step denoted by u of t, uh, right? What is its Laplace? 1 by s.
1 by s.
So then you have unit ramp. So this should be r of t, correct? So it has a Laplace transform 1 by s squared. Then you have the unit parabolic, unit parabola. So this is right. There is actually no uh, unit for that. Simply we can write even the r of t here. Laplace is 1 over s cube. Okay. So also we might use the impulse if required, because signals and system we studied the impulse response denoted by delta of t, right? So anyway, there is no representation, could be just one, all right, but it is at a specific point, say t equal to 0. It's defined only at one. So we have to use all the three signals. True, right? So actually, the delta of t has another part in the definition, right? If you remember, it's delta of t is equal to 1 and integral 0, integral minus infinity to infinity, delta of t dt is equal to 1. That's the actual definition. Okay. So it is defined at only one point and it has an area equal to 1, right, at that point. That's what is the definition. Anyway, fine. So we have to use the first three signals, and we have to define what is the steady state error. This is required because we already have discussed that we want to modify or model the whole system's output to any disturbance in terms of these three signals, right? That's why now also we stick to the same. We try to analyze the whole system's response, right, using the three by uh, representing the inputs using the three and calculating what could be the steady state error. Okay, so the first part is ess for step input. Okay, So step input r of t is what? It is u of t. Step input. So what should be the r of s? R of s should be equal to 1 by s. Right? So just now we calculated the steady state error in terms of the Laplace, right? So this is limit, say s goes to 0. This is s into r of s whole divided by, this is 1 plus g of s into h of s, isn't it? So this is the equation we just obtained to calculate the steady state error. Okay. Under this condition, now let's substitute the r of s, right? This is limit s tending to 0. This is s into r of s is 1 by s, correct? Whole divided by 1 plus g of s into h of s. So s cancels. So the limit actually goes only to the denominator now, because that's the only term which has the s in it, right? So 1 plus limit s tending to 0. This is g of s into h of s. So in the literature, various textbooks call this part, that is limit s tends to 0, g into h, as a specific error coefficient. This is called as a kp. So this becomes 1 divided by 1 plus kp. So this is the steady state error of any system, right? When the input is u of t, right? So where the kp is simply limit s tending to 0. This is g of s into h of s. Anyway, g into h will be known as soon as the system is given to us. So directly, without calculating the output in time domain and then calculating the error and then going for a kp, we can directly calculate by just using limit s tends to 0 g into h for a system to calculate the error coefficient. So this has a name now. The p indicates the position. Okay, so this is positional error constant. So this is the positional error constant, okay, of a system. So just we need to remember, when the input is unit step, the error becomes equal to this, and kp is given by limit s tends to 0 g of s into h of s. Okay, so we look at the we check the first signal and what happens, how to calculate the error, steady state error, we understood. Okay, now we'll go for the second system, second input to the system. Now ESS, when input is a RAM. Okay, so RAM signal is simply R of t is equal to t, correct? So this means, what is the R of s? Laplace transform is 1 over s square. Let us calculate the ESS now. So ESS, let's write the definition first. So this is limit s tending to 0. This is s into r of s whole divided by 1 plus g of s into h of s. Okay, all right. So this implies, now, so this, therefore this is equal to limit s goes to 0, s into, what is r of s? 1 by s square divided by, this is 1 plus g of s into h of s. We can see that the one of the s will cancel. So the s can be written in the denominator as this is limit s tending to 0 1 over this is s plus s into g of s into h of s. Okay, fine. Now, okay, now you see the this limit goes to both terms in the denominator, right? But when I apply limit s tends to 0, what is this part? 0, right? Because s is 0, right? But I cannot say that s into g of s into h of s becomes equal to 0, right? This is because there in the g of s, I have some numerator, some terms, but denominator could be s into something, correct? In that case, this s and this s will get cancelled, and I still have the g of s into h of s as a finite value. It's not 0. Okay, so because of that reason, we are not allowed to cancel the s into g of s into h of s simply because s goes to 0. Okay, so for that reason, what we do now, this is equal to 1 divided by, this is 0 plus limit s tending to 0, this is s into g of s into h of s. We are not going to make this 0 simply because s goes to 0. So again, in the literature, you can see that this term is what is defined as kv. Okay, correct. Right. So that's right. So ESS becomes equal to, now it's 1 divided by kV. So this is the second type of error that arises in the system when the input is a ramp function. Okay. All right. So further, okay, let me define what is kV. So this is where kV denotes, kV is first, let's give a name for this. kV is called as the v for velocity, constant or coefficient, right? So this can be calculated as kV is equal to limit s tending to 0, this is s into g of s into h of s. Now, if you look at the Kp and Kv, we have the s which is present in Kv, which is not present in Kp, right? Uh, so, in order to denote what type of differences they have, right? The word position and velocity are actually used physically, right? What is the physical meaning of the Kp Kv? There is no velocity over here. There is no position over here. Okay, they use the words velocity and position just to denote the relationship. Okay, uh, no, in case of a system there is no movement actually, right? So right, so but the words velocity and positions have been used just to relate them, show the relationship. You see the relationship is the kp you are calculating simply as g into h, correct? So limit s tends to 0, g into h, whereas the kv you are calculating s into g into h. Correct. Now, how they are related? What is S? When you multiply by S in the S domain, what exactly happens on the time domain? I think maybe the previous class we discussed about that. Just I'll show you something. Uh, I think the second problem itself. Yes, yes, yes. You see here, right? When you multiply by S to some function, what happens on the time domain? What is this? Differentiation, correct? Now, what is the relationship between displacement and velocity? what is the relationship between displacement, say x is the displacement and v is the velocity? How do you relate them? Velocity equal to dx by dt. That's what is happening here, right? So this is called kp, position or the distance. This is kv, right? So kv is should be, right, kv should be somewhat related to the kp as dkp by d whatever variable, right? So that's why, so if you take this is gh, this should be s into gh, correct? That's all, right? There is no physical movement, there is no physical velocity, just to give a, yeah, relationship. So if we remember in terms of, okay, this is displacement, the other one is velocity, then there should be a multiplication of s in the s domain. Okay, so that's the only reason why it's called by this name. Okay, so names are given specifically for that reason. Okay. Okay, okay. It's not in that way, right? So directly they are related. But now you understood, right? Because since there is a s present over here, it means, right, directly you are relating to the kp, right? Multiply kp by kp, whatever kp you are calculating by using g into h, multiply by a s and take the limits. Right. So this is how you calculate the response of a system when you have the ramp input. And now we need to go to the third input, that is the calculation of steady state, right? ESS, when the input is parabolic. So now directly we can write, we know what is the R of S. This is equal to 1 divided by S square, S cube, right? Sorry, my mistake. S cube. By S cube is the input. So let's calculate the error steady state using the same equation. This is limit s tending to 0. This is s into r of s whole divided by, this is 1 plus g of s into h of s. So this means this is equal to limit s tending to 0. So this is s into 1 over s cube divided by 1 plus g of s into h of s. All right, so this is now s and cube cancels over there with the s square. The s square goes to denominator, so this is limit s tending to 0, 1 divided by s square plus s square into g of s into h of s. Okay, so this is now 1 divided by the s square directly becomes equal to 0 plus the limit as s tending to 0, this is s square g of s into h of s. So g into h simply is kp, right? Then what should be s square into g into h? Because just now we understood that g into h is kp, s into g into h is kv. So s square should be, it's a double differentiation, right? S is differentiation, S square is double differentiation. So when you have a position and differentiate that twice, what do you get? You have distance, distance by time is velocity, right? So so velocity by time is what? Because you are differentiating that once again. Sorry, acceleration. Perfect. So this has to be a ka, right? So this is 1 by ka. So when the input is a parabolic input, so the error becomes, steady state error becomes 1 by ka, where ka is the acceleration error constant. Ka is equal to limit that s tends to 0. This is s into s square into g of s into h of s, called acceleration error constant. Is it okay? All right. So these are the three different types of what you call errors that exist over this. Now, there is another view for the calculation of this error by looking at the g into h, because everything depends on the g into h, right? As we already we have seen, we are not cancelling this term, right? Since s tends to 0, right, s square g into h we are not cancelling, because already you know that the g of h could be g into h could have something to cancel the s square, correct? Okay, so that is what is uh, called as the type of the system. So let's try to write one thing now. So this is called as type of systems. So the type of system, let's say the g of s into h of s can actually be written in several formats. Okay, one such a format is actually called as the pole zero format. Okay, in the pole zero format we can try to write it in the following notation. This is k into, so this could be s plus numerator is 0, correct? So z1 s plus z2, there can be several zeros over there, and also the system can have several poles, right? So this could be s to the power n, you can have multiple numbers, then s plus pole p1, s plus p2, etc. In the factorized format we can write in this particular notation. This kind of representation is a transfer function. This kind of representation is called as the pole zero format. In pole zero format we can write this in this way. What is the other format? Are you able to recall any other format in which we try to write the transfer function? Hmm. True, true, true. No, always it's like that. So the most familiar format is this. We have for a plotting purpose we use this. But if you remember, right now we are discussing the system and the properties of the system in time domain. Okay, but if you shift into the frequency domain, right? You might recall we might have studied the frequency domain analysis of a control system, right? By looking at the plots, various plots like Bode's plot, Nyquist plot, or any other plot, correct? So for plotting purpose in frequency domain, we use another format that is called as the time constant format. Have you come across that? So I'll just time constant format. So there is another format. Just let me write that here. So since it correct. So g of s into h of s. What we do here, you take the z1 outside. Okay. So when the z1 goes out, there is 1 by z that is coming here because you are taking the z out, right? So that looks like a time for you, right? So this is the same term. I'll write a different constant now. So this I'll write as k dash. Okay. So k dash into this is 1 plus s into tau 1. Okay. So this is 1 plus s into tau 2 and so on divided by. So in the denominator also you might get the there is a Correct, correct. So this is 1 plus s into, I can write this is say tau A, 1 plus s into tau B, and so on. So now you see that there is a time coming into picture, right? Why do you need this? Because if you want to go to frequency, right, it's very simple. Take 1 by time, it becomes frequency. So our plots are going to be in terms of the frequency. So if you want to write plot something in the frequency, I need a time term over there. I don't want the physical distances like z1, z2, p1, p2. I don't want. So you just convert into this format because of that reason. Since the plots are basically frequency versus magnitude or frequency versus angle, etc. Right? So one axis is fixed as a frequency. Correct? So you need some terms either directly in terms of frequency or in terms of time so that you can convert the 1 by time into the frequency. Okay, so this is called as the time constant format. So both formats are widely used in the control systems analysis part. So specifically pole zero format in the time domain, time constant format for the frequency domain. So frequency domain we'll see later, right? Once we finish this stability in time domain. Okay. Now, so you can see in both the formats, I have a denominator s to the n common, right? S to the n. So the n value denotes when you, it's specifically when you write as a factors, denominator has to be factorized, right? I cannot simply write like the denominator as s cube plus 2s square and so on. Now s to the n is not the one which we are talking about, only when you factorize. So you can see that it's already been factorized, s to the n into something, 1 plus s tau, 1 plus s tau b, and so on. So the first format is 1 plus sp, sorry, s to the n into s1, s plus p1 into s plus p2. It should be factorized. Okay, only when you factorize in any of these formats, right, whatever the n you can see over there, that is called as the type of the system, right? So the s to the n basically denotes what is s to the n. Can you tell me what is this s to the n denotes? No, no, no. In general, see that it's present in the denominator, correct? So denominator terms, when you factorize, you get the position of poles. Now s to the n in the denominator. So this indicates what? S to the n. When I say s to the 4 in the denominator, right? S to the 4 into s plus 4 plus s plus 6. Huh, number of, correct. Number of poles at where? So if I have a term, see, if I have a term called say s plus 4 in the denominator, you will equate that to 0 and say that there is a pole at minus 4. Similarly, equate this to 0. When you see s to the, when you equate the s to the 4 to 0, right? What do you get? S is equal to, so my question is this. So I have say n equal to 4. I have s to the 4. I equate it to 0 to find the position of poles. What is the answer? S equal to 0 comma 0 comma 0 comma 0. Four values are there. All the four values are zeros. Right? So s to the n indicates n number of poles at origin. Correct? Is it right? Huh. So correct. Number of poles at origin. Correct? This itself is what called, where the n is now called as, it's not the order, because there is a difference between order comes into picture when you write, when you don't have a factors, right? You don't have factors in the denominator, you simplify the factors, you multiply and get some term. Now s cube plus 6s square plus 9s plus 12, the order is 3, correct? Then you, whatever you get is the order, right? See, right, but that is not true in this case. This n is not that value, because you multiply this with this, you get one more s, right? S to the n plus 1. See, the s to the n plus 2 and so on. You have more number of s coming into picture when you multiply the brackets. Okay, so now this n is different, right? When you factorize and write that as a s to the n in the denominator, the n is said to be the type of the system. So type and the order, they are different. Okay, type of the system. So what exactly type of system represents? The number of poles at origin for a given system, right? So if the system has two poles at origin, the type is 2, right? But order is not necessarily 2. Order could be different. Okay, all right. So now we are actually looking at the types of system which actually represents the number of poles at the origin for the given system in terms of G into H. So now what we do, we understood the different ESS, steady state errors, we understood. Okay, we also have discussed about the types of system in terms of G into H. Now we analyze what happens to the steady state error when the system type changes. Okay, so ESS for type 0 system. Okay, so type 0 system, let's calculate. So what is now type? When I say type 0, what should be the G of S into H of S? Let's write in the pole 0 format. Okay, so this will be a constant K multiplied by S plus Z1, S plus Z2, and so on, divided by, this is S. Now you see this is S to the 0 outside. So because type 0 means n equal to 0, right? N equal to 0 means s to the power 0 in the denominator into s plus p1, s plus p2, and so on. Now you see, calculate what is the, for a type 0 system, if input is r of s is equal to, so if r of s is equal to 1 by s, what happens to the ess? Already we have calculated. Ess is equal to, when the input is 1 by s, what is the 1 by 1 plus kp? Now, which means I need to calculate a kp now. What is kp? Kp is equal to limit s. This is simply g of s into h of s. Apply this. G of s into h of s is this. Correct? In that, if you put s equal to 0, all these terms will get cancelled. Right? Those terms will not be present. So when you don't have those terms, it's simply k. Correct? So Kp is a K from the above equation. This is a constant. Correct? When that is a constant, so this is 1 by 1 plus K. This could be a constant. In the sense, for a type 0 system, if you give unit step as an input, then there will be a finite error in the final output or the steady state. In the steady state condition, you are going to get a constant value of error. Right? Let us say for the same system, I'm going to give input r of s is equal to 1 by s square. Right? So whenever input is 1 by s square, what is the equation for ESS? ESS has to be 1 divided 1 by kV. Right? So 1 by kV. So first let's calculate what is kV. Therefore, kV is equal to limit s tending to 0. This is s into G of s into H of s. Correct? So G of s into H of s you have. To this you multiply by a s. So this into s. Correct? Now you see there is no s in the denominator to cancel this s. Correct? So I don't have anything. So this means what happens to the kv? Kv becomes equal to 0. Right? So this means I'll write here. So this is equal to 0. The kv becomes equal to 0. So 1 by kv means this is 1 by 0 infinity. Correct? Are you okay? Which means for a type 0 system, if you give a ramp input, the at the output, final output, in terms of the steady state, there will be infinite error. Are you fine with it? Okay. Now let's change this. If say R of s is equal to 1 by SQ, what happens to the steady state? ESS is equal to, now this is 1 by KA, right? So 1 by KA, where KA is equal to the limit s tending to 0, this is s square into G of s into H of s. So for the same G into H, you multiply by s square. Now you can see that there is no s in the denominator to cancel this. So as soon as that comes into picture, right, there is a s square which you are multiplying. So s square is 0. So s square into whatever G into H you have, this becomes equal to 0 now. So once again you get 1 by 0, right? Because when you try to calculate the 1 by Ka is 0 now. Correct? So when the Ka becomes equal to 0, 1 by Ka becomes infinity. The error when the input is a parabola. Parabolic input is given to a type 0 system. Ka becomes 0. Okay, now, so ESS of type 1 system, right? So in type 1, what's the representation? So G of S into H of S will be a K into, this is S plus Z1, S plus Z2 whole divided. Now you see there is a S coming. So S into S plus P1, S plus P2 and so on. So since you have the S in the denominator, S to the power 1 comes over there, which means there is one pole at the origin. So now let us calculate for different inputs like we did earlier. For this system, if put R of S is equal to 1 by S, then what happens to the ESS? ESS is equal to 1 by 1 plus Kp. So what is Kp? Kp is equal to limit s tending to 0. This is G of s into H of s. Now G of s into H of s, we will make sure that this, I have to put s equal to 0 here. So this becomes 0. So denominator becomes 0. Denominator of G of s into H of s is 0, means the whole term becomes infinity. So Kp is infinity. So this is 1 divided by 1 plus infinity is 1 by infinity. So that is equal to 0. So now you see, for a type 1 system, if the input provided is unit step, there is no error. For a step input, Type 1 system, you get exact answer. Whatever is required, you are going to get. There is no error. That's what is the meaning of this. Okay, so if R of s is 1 by s square, we know that ESS is equal to 1 divided by kV. So where the kV is nothing but this is limit s tending to 0, s into g of s into h of s. So when I multiply the g of s into h of s by s cancels. So only it's a constant now. When you substitute all the values, you get a constant. That's a k. So s into g of s into h of s becomes equal to k. So this becomes kv is k 1 by k. So this is a constant. So when the input is given as 1 by s square or a ramp to a first type system, output the steady state error becomes a constant. Okay, and the last case, if R of s is equal to 1 over s cube. That is, we give a parabolic input to type 1 system. So we know that the steady state error is already calculated. This is 1 by Ka. But let's write what is Ka first to calculate this. This is limit s tending to 0. This is s square into g of s into h of s. So I know that when I multiply this with the s square, right, one of the s will get cancelled, one s still remains, and that s is 0, correct? So g into h becomes equal to 0. So when as s tends to 0, this is 0, so this means it is 1 divided by 0. That's why it is infinity. So you have infinite error in a type 1 system when the input is parabolic. Okay, so fine. So, okay, there is one more thing remaining. You try to derive that by yourself, and we'll discuss the answers in the next class. That is, the ESS type 1 is over, so you should do the type 2. Only till here works because most of the systems are up to this. Practical systems are type 0 or type 1 or type 2. Okay, so this part, same thing you repeat once again, right? For you give the different inputs, 1 by s, 1 by s square, 1 by s cube, and calculate what are the possible ESS.